Okay, hi guys, thank you for joining. And we'll start the session. I'll share my screen to the Jamboard first. Share. Alright. So, first, I'll be telling you some concepts. Cool, then we'll go to some tricks. I'll tell you some STL functions as well. That will be very limited though. Some data structures, right? Then we'll try to solve a few problems. We'll break it down. Okay, we'll see how we break down problems. Cool. So, there are quite a lot of things that I'm going to talk about concepts, and the first thing that starts with is when you try to solve a problem. Okay, like say there's some problem, it says ki, okay, the array is rotated k times, right? And yeah, the concepts or things that I'm telling you that might be oral. If there's something to write, I'll write it down. If there's something to code, I'll share my VS code as well. All right, so okay, we'll come back to that again. So say you have a question where you ask like the array is rotated k times, right? And n, the length of the array is given, say 10 raised to the power 5, right? So it's obvious that you cannot rotate it that many times, right? Say k times k is also 10 raised to the power 5. So if you try to rotate array, every time you rotate an array, you shift all the elements, so it takes O of n, right? So basically, you cannot afford O of nk, right? So in that question where it says that okay, you are given an array of length n, and it is rotated k times, you can never simulate the question, right? You cannot just rotate it k times and check like what the answer is. Say whatever they're asking, it doesn't even matter. You cannot do that, right? So the only way to solve these kinds of problems are you have to break it down. Okay, like there are problems where if for the same n, okay, the time complexity might be something like n raised to the power 4 if you try to simulate it, right? So you don't really have to simulate it. Even in problems where it might still be on, try not to simulate it. Try to find a very uh, broken down solution for everything, right? So there are problems where very big long stories are given and the answer might just be maximum of the array that's given in the input, right? They make questions like this. So learn to break down problems. Don't try to simulate the complete thing, or just how do I say, just say what, just code whatever is given in the question. Just you're trying to simulate everything, then checking. Okay, it works in some problems. We'll see one problem like that, but that's not always a good idea. Okay, not always, but sometimes you do have to do it. Okay, then mm, also I saw a lot of you are using Python, and one of the mm, students who registered did this mistake, like know the time complexity of the inbuilt library functions you're using. Don't just blindly write everything, okay? And never, and you're not realizing like what time complexity it is, right? So something like in Python you have something like a bool condition, like if x is in something or if y is not in something, right? Understand how this works, understand what is checking in or not in, right? Understand what the time complexity is. If you're checking something in a linear data structure like an array, right, it's pretty sure it's going to be O of n, right? But again, if you're for the same thing, if you're checking something in, say, data structure that corresponds to a balanced binary tree, like again, I cannot say for sure for Python, but say sets or maps in C++, those are balanced binary trees. So searching on them will be like binary searching. So that corresponds to log of n. Okay, so what time complexity is it is not the main thing. Thing is know whatever function you're using, know the time complexity of it, right? So you cannot just like somebody wrote a program like okay for and if not in, then inside again you say okay if not in again, if in again, and these are not constants. These will keep on multiplying if the time complexity is in, right? So even if it doesn't look like it's such a high time complexity, it might be, right, deep down. And only use those functions that you know, library functions, right? And in Python there are like tons of functions, and not even functions, even like you like the syllables that you write that might have a time complexity overhead. So know what you are writing and know the time complexity behind, right? That's why in C++ you'll see a lot of things are memory based, like linear, either linear based or they are inside the data structure. So you should first go and read about the data structure that you're using, then use their functions, right? Like in C++, you already have something called lower bound, which is basically binary search. So you can always do set dot lower bound. I'll just write LB, and you can say give a value, say 15, right? And it will give you what is the any number in the set that is greater than equal to 15. Basically, it will binary search the set for this number. So you have things like this, but know the time complexity of this. This will again binary search it, so it's log of n, right? Okay, just the main idea is whatever you're using, whatever library function you're using, make sure you know the time complexity. Don't blindly use it. If you don't know the time complexity, try not to use it. If you have to use it, go learn about it first, right? Apart from that, Python people don't need to actually worry about this, but you should know the constraints of the data types that you're using, right? And people who have coded some lead code problems in C++, they realize is that sometimes you run into errors where they will say unsigned integer overflow, right? And it is really very easy to miss that. Say in a question it's given. So I'll tell you, like the integer data type in C++ has 32 bits, right? So that stores a number in this range, right? Or it's 31. Just leave. Okay, something close to this, right? So that is something close to 10 raised to the power 8. It depends on what you're using. It's signed or unsigned. Cool, but it will always be around this 10 raised to the power 8, 10 raised to the power 9, actually. So every time if you in a question, if you see that you have to calculate the sum of the array, say in it's asking for some sum, okay, the like the answer you're going to find involves finding the sum, and say the size of the array is 10 raised to the power 5, right? And the elements in the array can be up to 10 raised to the power 7. You can clearly see that if you sum the entire array, give me a second, if you sum the entire array, you're going to get a sum that is multiplication of these, that is 10 raised to the power 12, right? And you'll always overflow the integer limit, right? So make sure in the question you see if you are going to sum it, what can be the maximum sum? Will it fit in your data type that you're using? If not, always make sure you use the required data type, right? So in Python, this is not a problem, okay? And even while modding, you won't get a lot of problems, right, when you're trying to mod, because in Python the length of the data type is not really a factor. You can have very big lengths without even worrying about it, right? But in C++ this is a thing, and I'll prefer you to at least learn about it, right? Even if you're using Python, learn about constraints of values for different data types and what problems can they cause, or how do you handle them, right? Because even if you're using Python right now, when you'll go and develop applications, not all languages have this facility of having an infinite length data type. You'll be limited by the number of bits that is composed in that data type. So you need to learn how to handle constraints, right? So know to break down the problem and see what is the maximum value that you can get in a variable, okay, in your program. No matter what you're doing in the program, no matter what algorithm you're using, make sure you know what is the maximum value that you can get. Like in Dijkstra, say when you're calculating distance between a node and another node, okay. So say there are 10 raised to the power 9 5 nodes, and each distance can be 10 raised to the power 9. You can easily see that it will go up to 10 raised to the power 14, right? Which will of course overflow the integer limit. So make sure you handle it, right? Make sure you see these things in the program. Always look out for these things in the program, and also you have to look out for like what time complexity to use. So a general rule of thumb is, if it is something close to 10 raised to the power 6 or 7, okay, you can always use O of n, okay, because roughly in modern compilers 3 into 10 raised to the power 7 is roughly 3 seconds, okay, or you can say 10 raised to the power 7 is 1 second, right? But again, that depends on compiler, depends on how much it's optimized, okay. But you can take this as a rule of thumb, okay. If you are given 10 raised to the power 5, you can do n. Here sometimes you can do n log n as well, okay. In 10 raised to the power 6, n log n might be possible, but it depends, okay. But again, log n is not a very big factor, and in most of the OAs I cannot be very sure of, but in most of the websites like LeetCode and Codeforces, they do have they do keep space for log n as well, right? Even in OAs actually, they don't really mind the log n factor. Sometimes in OAs, like even if you need a ON, sometimes ON square also works because they don't have very hard tests. That is a very different topic though. Let's leave that. So for 10 raised to the power 5, you can use something like n root n as well. Because if you compute this for n is equals to 10 raised to the power 5, it will come something close to 2 into 10 raised to the power 7, which again passes. Again for 10 raised to the power 3, you can do an n square, right? For 10 raised to the power 2, you can do n cube, right? So anything that comes below this, okay, works. Like any polynomial, okay, anything that you are writing n raised to the power k, where if you put n and k, and it comes below this, will pass the question, okay, will pass the time constraint. So that is how you find what do you have to use, like what time complexity, what polynomial can you use, right? So again, if it's given 10 raised to the power 3 and is 10 raised to the power 3, you can be pretty sure that you can use 1 square, right? Cool. Okay. Like in C++, what we do is to overcome the integer constraints, what we do is we just write, we have a preprocessor directives called define. Basically, it just picks all the words and replaces it with whatever you want. So we can write define int long. So it basically, what it does, it makes all the int long. So wherever you written right int a, right, it will just convert it to long a, right? So basically it again, you don't necessarily have to worry about any overflows above 10 raised to the power 9, but again you have to worry about any overflows above 10 raised to the power 18, which is the limit for long data type in C++, right? So this might again come in modulo problems. Okay, in modulo problems, like you have to do a into b mod some mod, right? And if again in modulo problems, you have to be very careful about again what values you can reach. Here, if both a and b are sum, okay, and each sum was say 10 raised to the power 14, you can see that this can again reach, this can even cross the long limit. Like then you have to do a mod b into b mod b, and again brackets whole mod. So that's modulo arithmetic, and that is a very different topic. But again, my main point is know the constraints. Okay, know what constraint each variable can reach in your program. Don't ignore it. Okay, when Python it's fine. In C++, you'll get a lot of problems, and even in any normal development, you get a lot of problems. So if you want to write a bug-free code, know what the constraints are for every data type that you are trying to use. And also things like float data type isn't accurate, right? If you have read about this IEEE format for storing float, you will see that float is always stored in something like this 1 plus 2 plus 1 by 4 plus 1 by 8. Basically denominator is a power of 2, and using this you can never get a perfect decimal number, right? So that is one thing, that is how float is stored. So never rely on float, never rely on floating point calculations as well. Okay, until you are, like if you have to be very precise, you can never rely on floating point calculations. So if you want to compare something like a by b, give me a second. Yeah. So if you have to compare something like say a by b is less than c by d, don't use fractional comparison, right? Don't do like this, a by b c by d. It might not be accurate because float is never stored accurately. Okay, instead do something like a into d is less than c into b. Always remember this. Then again, when you're multiplying, take care of the constraints of the data type, right? So never do this, always do this, right? So you will see this in a lot of problems where you have to greedily sort an array. Okay, say you have to sort the array on the basis of, say, somehow the problem asks you to sort it on the basis of ai by I. One second. Yeah, say the problem asks you to sort the array in the basis of ai by I. So you don't write the custom comparator and sort it base of that. You always sort it based on ai into j is less than I into a of j. I just cross multiplied like this, right? So always remember that floating point comparisons are not accurate. Okay, because you cannot accurately compute a floating point number. Okay, computers cannot accurately compute it. So you always try to stay in integer domain because integer numbers are always accurate. Okay, they are accurate to every number. Okay, so always stay in integer domain while comparing two numbers. Mm, all right. Again, like this depends because in DSA everything is accurate. Like in DSA, answers do exist, right? If you're doing something like machine learning, then a very small change in decimal points don't really matter. But in DSA, it will matter, right? If you say you can try this in a problem where something like this is required, and you'll see that again it depends on test cases. I'm not telling you it will fail 100%. Okay, it depends on test cases, what test cases they have made. But it usually, if you are submitting it in say lead code or code forces where the test cases are really very strict, that will fail. Okay, so always remember floating point calculations, floating point comparisons aren't accurate. Okay, so always keep those in integer domain. All right, now mm, all right, now this is a very small thing, and it doesn't even really matter if you want to do it or not. Say you are trying to find prefix sum, or you are trying to use some kind of DP, right? So say for prefix sum 0, 1, 2, 3, 4, 5, you have some numbers 1, 2, 9, 11, 15, 2. So what do? For this, you add this to this, so it becomes 3. You add this to this, becomes 12, and so on. Right. So what do you do for 1? For 1, you cannot add something, right? So you put that check that, okay, if I is 0, you do not add it, else you add it. Now what happens if it's not a one dimensional data structure, if it's two dimension, then you have to put multiple checks, right? Because you can go out of it. So instead of that, you can just pad it. Okay, instead of this being 1, 2, 9, 11, 15, 2, you can just have it like 0, 1, 2, 9. Right, it's a very small change. Might not sound like a very big trick, but it saves a lot of implementation issues and a lot of debugging. Okay, so you can always start from here and again add 0 to 1, won't change anything, of course. Then you can just do the normal thing. You'll eliminate a lot of conditions, and in problems like what is the problem? Longest common substring, longest common subsequence. You'll see that it eliminates a lot of options. Actually, you don't have to worry about coming to that null part, right? Where this I minus one doesn't exist, j minus one doesn't exist, I minus one, j minus one, I j minus one, I minus one j. All those you don't have to check anything. You can just pad it with zeros, and just you can do a one-liner for whatever DP relation you get. Right. Again, this is a very small change, but if you're trying to write code fast or quickly, like during live coding rounds, right, you do need this. Okay, you can just pad it quickly. Then you don't have to worry about, like in live coding rounds, they do check like how you're handling the conditions, like corner cases and things like this, where you might go out of bound, right? But there, if you just pad it and say that okay, I'm padding it to control this, then you will save a lot of time for yourself as well, and you'll get a lot of time to think about the original answer, right? So this might not seem a very big thing right now when you're solving, because right now writing extra if conditions takes hardly what 1 minute or thinking about it, right? But in interview it will take a lot of time and a lot of your mental space as well. So if you have habit of writing things neatly or more optimally, where do you have to think less, that will always help you in live coding rounds. Same goes for how you break down problems, right? So if you can always break down problems to the simplest level, okay, that will always going to help you. Again, I am not asking you to directly come to the optimal approach. It's not possible. Okay, even during your live coding rounds or interviews, you are not expected to directly jump to the optimal answer, right? You must first give the brute force. Okay, this is what we can do, and brute force can always or many times be simulation. Okay, always give, okay, we can simulate it, then we can check it, we can greedily check it, we can take maximum of the entire array, check it, rotate maximum entire array, check it, anything, any, if this corresponds to any problem. Okay, but then you have to refine your idea. Okay, like okay, maybe taking maximum every time, maybe you can pre-compute it and take maximum of ranges. Then you have to keep refining and come to one optimal idea that is the breakdown of the complete problem, right? So practice this in whatever problem you are trying to solve, there will always be a very small idea that solves it. Okay, most of the lead code easies can be solved in 1 or 2 lines. Okay, and if you are writing more than that, there is a shorter idea possible. Try to think of it. Even if you solve a problem, try to think how you can solve a problem in a shorter way, in a concise way, right? So it's not always about just solving the problem and getting the passed or accepted, right? If you can always break it down into more concise format, it will always help you during interviews or in OAs everywhere, right? Always, like when you, it's called like post thinking, post submission thinking. After you submit a problem, you again come back to the problem and think about how you can improve it, right? And that's a very good thing. I do it a lot of times. Every time I submit a solution, I think about it like, can this be solved with something else? So there are problems that I've solved like in 2 3 different ways. It's a very good idea to do that, right? Always break it down. Always try to keep breaking it down, keep breaking it down. Say you have a 2D DP, you can always break it down. If possible, you can find some relation that falls into some pattern, and you can always make it into a linear DP. Not always, you can make it, like there are problems like that where you can reduce a 2D DP into a linear DP, right? So always do that. Or even do the post submission analysis where you can you break it down more, right? Can you think of something else? Or a better thing will be to ask someone, okay, that does a better solution exist? Or you can go to the submissions. What how I learned things was, usually after a contest, even in the problems that I got accepted, I would go to the leaderboards and check like first 10 solutions for the same problem. People, like first 10 people, I check their submissions and how they coded, and I check like how they think, and then you'll find a lot of difference between their code or your code, right? Even though both of you have passed the question, you'll see that they wrote it in a much concise manner. Might not be more understandable, right, to you, but for them they have broken it down in such with such simplicity, like in the idea is such straightforward. But see, it might be hard. Now there is this thing with that. If you if you are doing most of the work, like you are thinking a lot for a problem, you're breaking it down to a very small idea. That idea will be very hard to understand for someone else, but for you, if you understood it, it will be very small to code, right? So basically this corresponds to, if you are doing more work, the machine has to do less work, right? And if you are doing less work, the machine has to do more work. That just goes with the time complexity stuff as well, right? So if you are not writing a very optimal algorithm, machine has to do something like n square, right? But if you're writing a very optimal algorithm, you are thinking a lot, machine just has to then do an O time complexity, right? So that's what. Cool. Okay, so I think we are done with concepts. So I'll just tell you some tricks now. Okay, and again, these tricks are mostly programming oriented, right? And might it things might be a bit different if you use different programs, but I'll try to stick to general idea more. Then I'll come to STL for a while. Okay, now again, I want to talk about sealing a value. So you might have known about this function that exists in your math library called seal, right? And what do you pass in seal? You pass a float value, right? And what do you get? You get the next integer value, right? You get an integer value that is greater than or equal to this number, right? So you pass 3.1, you'll get 4. You pass 4, you get 4, right? Now what did I tell you about floating point? It's not accurate, right? So what happens if you pass a seal of a by b, which you thought is 3 point some 015 and should have corresponded to a 4, but somehow this was stored at 2.995 and it corresponded to a 3. So you see that's wrong, right? This is wrong. Why? And why was this wrong? Just because floating numbers are not accurate, right? So instead of using seal, I'll give you a better way. I'll bring the seal function in integer domain. Okay, so basically how do you compute a by b in integers? Okay, say both a and b are floating point integers, they are not floating point numbers. So something like 3 by 4. How do you seal it? You basically add some number here, right? Something like 3 plus something, and then you do a by 4. Basically this is what sealing is, right? So what do you add here? You basically add whatever is remaining for 3, or let's write whatever fraction you have as this form, say a b by c. So just remove the whole number. Okay, well, whatever whole number you have, you just remove it, right? Then for b by c, if this is b by c, 3 by 4, you add whatever is remaining to reach 4, say 3 plus 1, and then you do a by 4. So this is a, what do you call it, integer division. Okay, remember, I'm doing integer division. Python people, I'm doing integer division, right? So then you get 1, right? Now, what happens if you add something more than 1? Let's say you add 3 and not 1. What happens when you add 3 plus 3 by 4? You again get a 1, right? So what I am proposing is, instead of doing the ceil function, how about you do something like this? 3 plus 4 minus 1, right? So for general form, a by b, ceil of a by b can be written as a plus b minus 1 by b, right? Now you'll say, why are you adding b minus 1? Now look at this, what should be 1 by b ceiled to? 1 by b should be ceiled to 1, right? So what happens if you add b minus 1 to 1? It becomes b by b, which gets ceiled to 1. Now again, what should 0 by b be ceiled to? It should still remain 0. So what happens if you add b minus 1 to 0? It still remains b minus 1 by b, which is again a 0. So by adding b minus 1, you are actually sealing the numerator, right? So this is that easy. You brought the ceil function to integer division. How? For ceil of a by b, just use a plus b minus 1 by b, right? Now this is any, you can have it as any representation, not just whole number, right? Even if a is a lot bigger than b, say 112 by 15, the ceil of this will always be 112 plus 14 by 15. This is integer division again, so this will always be the ceil, right? Now I explained you the proof. So the smallest number that can exist on the numerator that has to be sealed to 1 can just be 1, right? So basically 1 plus b minus 1 by b will always give 1, right? And this is what you wanted. Had it been 0, b minus 1 is smaller than b, so it will give 0, right? So this is one trick for ceil. So yeah, so never use the ceil function in your library if you're hoping for accurate answers, because again, see, what's the use of going from integer domain to, say, if you are dividing a by b and doing ceil and both of them are integers, what is the use of going from integer domain to float domain, then again sealing it to integer domain, right? You will lose precision, you might lose precision, right? So it's better to stay in the same domain if you are intending to get a number in the same domain, right? So always remember this, use ceil, right? But again, for negative numbers, remember, so for negative a by b, so what should be the ceil of minus 3.5, right? This is general maths, it should be minus 3 and not minus 4, right? Minus 4 is a number less than this, you are coming above it. So basically ceil of a by b minus a by b is again a by b itself, you don't have to add anything, right? So minus 7 by 2's ceil is 3. You just do an integer division, sorry, minus 3, you do an integer division, right? So you can just check where does numerator belong to. If it's more than 0, you add denominator minus 1, then do integer division, else you do nothing, you just do normal integer division, right, for the ceil, right? So if I share my VS Code now, yeah, alright. output is visible. Okay, cool. Output is visible in the recording as well. Okay, okay. So again, so how you can write a ceil function is int ceil, right? Int a, int b. So if a is less than 0, you return a by b, right? Else return a plus b minus 1 by b, right? So this is a ceil function. You can create one of your own and just use it like this, right? Again, cool. Now I think I need to talk about this, like shift operators. I have seen a lot of you not knowing how shift operators work. So shift operator basically, like, this is a different shift operator that you use in cout. It's passing this stream. Basically it does the same thing, right, but in a different way. Let's not talk about that. But I'm talking about something like int a is equals to 1 left shift 2, right? So for people who don't know, left shift operator, what it does, it in the binary form of this number, it shifts all the bit to that number that you are writing here. So 1 left shift k means, say, binary representation of 1. What is binary representation of 1? Say I'm just writing 8 bits, so it's this, right? So basically 1 left shift k means, or 1 left shift 2 means, this 1 will be removed and it will come here, right? And as you can see, every time you shift one space, what happens? The whole thing gets multiplied by 2, right? So basically writing a is equals to some number, then a is equals to a left shift 1 is similar to writing a is equals to a into 2, right? But there is one difference, and this difference is very big. The only difference is that all the bitwise operations, now understand, this is a bitwise operation, it happens bit by bit, right? Understand that all the bitwise operations are very fast and very optimized in compilers. Okay, so you will get a drastic speed improvement if you try to use bitwise operators. Other bitwise operator include something like XOR, okay, bitwise OR, bitwise AND, something like a is equals to a or 1, right? So again, shift operators. So using shift operators, you can multiply some number by some power. So a left shift 4 will be a into 2 raised to the power 4. So basically it will be a into 16, right? Something like this. So, and always try to use shift operators wherever possible. Say if you want to compare some number, if it's less than 2 raised to the power 32, okay, now what is 2 raised to the power 32? You can write it as 1 left shift 32, right? Again, take care of domain, the integer domain that you're talking about, right? So you can always check if a is less than 1 left shift 32, right? Cool. If you understood this, similar way you have right shift, right? So a is equals to a right shift 1 is similar to a is equals to a by 2. Yes, and this will be integer division. Now how will this be integer division? Say a was some number 0 0 0 0 0 0 0 0 0 0 0 0 1 1, right? So if you left shift it once, it becomes 0 0 0 0 0 0 1. So basically this last one disappears. Last one is responsible for your odd part, right? So this disappears and this just becomes a 1, right? So basically 3 by 2 is 1, right? So if a is 3 and if you left shift it by 1, right, it becomes 1, right? Okay, now I told something here. I told that the last bit of a number corresponds to the odd part of the number. Do you understand why? See, there is one number theory concept which says that even plus even numbers, if added to even numbers, will always give a even number, right? And even numbers when added to a odd number will give an odd number, right? So if you talk about bit positions, right, then you'll realize that all the bit positions apart from the first position is some power of 2, right? 2 raised to the power, even first to the power of 2, right? But let's not count zeros. Everything is 2 raised to the power of 2 something k, where k is greater than 0. Now what happens? All of these numbers are even. Last number is 2 raised to the power 0, which is 1. And 1 is the only odd number in the binary system. Right. So no matter what number you are composing, right, what number you are composing, if your last bit is 1, okay, just the last bit is 1, it is an odd number, because all other bits correspond to even contributions, right? Just the last bit will give you the odd contribution. So checking the last bit alone is sufficient to prove that a number is odd or even, right? Because only last bit will contribute to the odd part. So basically this number will be equal to 2 raised to the power 1 plus 2 raised to the power 2, both of which are even, right? So again, see if you can understand this. If a and 1, what does it tell you? So this tries to perform a bitwise AND operation with a. So here if a is 3, let's just write last 4 bits now. So 0 0 1 1, it tries to perform an AND operation with 0 0 0 1. Now tell me what should be the result of this. The result of this is 0 0 0 1, right? AND operation. Wherever you have same bit, wherever you have 1, you just write 1. Right, 1 and 0 goes away. Right, you need a 1 here to have a 1 here as well. Right. So what does this tell you? A and 1 returns you whether the last bit is turned on or not. Right. Right. Take a moment to understand this. A and 1 returns whether your last bit is turned on or not. Right. So you can always check for odd number just by checking the last bit. And to check for last bit, you can use the bitwise AND operation with a 1. Right. Now again, bitwise operations are fast. So where if in a problem you're using a lot of comparisons, this will always give you the best time complexity that is possible for that problem. Right. So okay, one more thing. Okay, and I'll just use this again. I hope you understand what AND 1 is doing. AND is a bitwise AND operation. It's not double AND. Double AND in C++ is this AND in Python. Okay, so I'm not using double AND, I'm using single AND. This is bitwise AND. It compares bit by bit. Okay, again, if you don't know about bitwise operators, you can go and read it. You can come back to this video again. Okay, so okay, tell me what happens if I do something like this. For int I is 0, I is less than some number 100, I plus plus, and I do cout I and 1. What do you think will be the pattern? Not 100, let's say 10. Let's actually run it. See the pattern. You found a pattern, right? It's alternating between zeros and ones, right? It's very obvious. Why? I and 1 gives an odd check, right? And odd numbers alternate, right? Even odd, even odd. So for a continuous series of number, if you do an odd check, this is the pattern that you are getting, right? Sounds very stupid, but how is it useful? Now say you want to, this is useful when you want to alternate between numbers, right? And it will be useful later on when we talk about space optimizations. So what happens when you try to optimize space? Say you are, say in dynamic programming, it's mostly used in dynamic programming. So let's forget what dynamic programming is right now. Let's just think that in dynamic programming, there are just two states that you want to take care of. Okay, one is 0 state, one is 1 state. So there is some relation in which the 1 state depends on 0 state, right, and 0 state depends on 1 state, right? So now what you want is, you just want these two states. You want to preserve these two states and alternate between them. So basically dp of 1 somehow depends on dp of 2, dp of 0, and then dp of 0 somehow depends on dp of 1, right? So again, let's just forget that it depends on something. So if you want to alternate between this, again you can use something like this. For int I is 0, so let's start with 1 this time. I is less than 10 and I plus plus, and dp of I and 1, this will give you 1 initially, is something. Let's add it actually, is dp of I minus 1 and 1, right? So what is I and 1 initially? It's 1, right? And what is I minus 1 and 1? It will be 0 initially when you start with 1, right? So 1 is taking something from 0, right? Now, let's say it's not, let's say it's 2 times whatever the last state is, right? So 1 is fetching its answer from 0, then again 0, in next iteration this will become 2, I and 1 will become 0, and I minus 1 and 1 will become 1, right? So dp of I, this will fetch its answer from dp of 1 now, right? Similarly this fetches from 0 and this continues. Okay, if you're not understanding this is fine, you'll understand it when you try to optimize dp, where you just need 2 states, right? And 2 states alternate among between each other, and this is how you can alternate them. You can use bitwise and make them alternate between each other, right? If this is too hard to understand right now, it's fine, we'll understand it slowly, right? So actually this bitwise and operator is very powerful in this. It's very powerful in optimizing space for most of the dp problems that we'll talk about later. Okay, now you might be getting bored. Now let's just see very basic things, very basic mistakes that you do, right? So say when you are calling a function, okay, and the function has to return something, right? Function has to return something. So a lot of you do something like this. If some condition, if something, okay, return true, else return false, right? You might be thinking, yeah, what's wrong with this? Right? There's nothing wrong with this, but can you see that you can omit this else? You can just write it like this, right? Again, that typing one else won't take a lot of time. That's not my point. My point is understanding how the flow works for a function, right? If this is true, this is always going to return true, right? If something is true, it will return true, and the only way the command of the function will come to this line is if this is not true, right? Because if this is true, this function terminates, it comes back here, this is not executed at all. If it is not true, if something is not true, then only it will come here and you will return false. So instead of writing if this else this, you can always omit this else. You can just write if this return to return false, that's all, right? One thing, very small thing, okay, but this helps you understand the flow of the program and flow of functions, basically how it goes here and there, right? Again, a very small thing and a very neat trick is that, say you are given 2 numbers, say the function has to operate for 2 numbers, int a and int b, right? And a lot of people do, if a greater than b, then do this set of functions, else if b greater than a, then do this almost similar set of functions, right? Let's say, so instead of writing this, just do something like this. If a greater than b, like the prerequisite of this function was that a should be less than b, so you just swap ab, right? Or you use your own swap function. There is a swap function in C++ itself. You just swap it, then do whatever normally you want to do, whatever similar set of functions that you are performing, right? Why do you have to write the same thing 2 times? See, increasing the length of the code will ultimately make it harder for you to decode if there is a problem inside, right? So always try to write clean, concise code, and that is what is appreciated during online interviews as well. Write a very clean and concise code that handles everything and is concise enough to be understood fairly quickly, right? So again, this is one thing, very small neat tricks, right? Again, a very small trick is that you might have heard about heaps, priority queues, right? So priority queues will maybe sort numbers or keep the smallest number in the top, right? Now what if you want to reverse the trend, right? So priority queue, if you pop priority queues, we have fed some numbers, and if you're popping priority queues, it will give you numbers in this format, say, right? Increasing order. So what if you want a reverse order, right? And say you are not writing a different iterator for the priority queue. So instead of writing a new iterator or changing everything, you store these numbers as a negative number inside priority queue. So in negative numbers, a trend of seniority based on level, based on uh, the comparison of elements, it changes, right? So then when you omit elements, it will come minus 10, minus 11, minus 19, minus 11, minus 10, minus 6, and so forth, right? Then again you can just pull it out and you can just make it positive, and then you can use it whatever you want, right? So again, instead of writing a whole custom comparator or just checking how to write it, because in C++ it's very hard to write a custom comparator for things like sets, priority queues, right? So instead of doing all that, just store it as a negative, right? This can be even used in Dijkstra in some form, right? This is one of the uh, variations in Dijkstra to store. We use priority queue, but we use negative distances, right? Again, just a very small trick, but it saves a lot of things. Okay, makes the code more concise and precise, right? Okay, and things like in C++, it might be there in Python also, but I think you have to typecast it. The true data type is always stored as 1, right? False is stored as 0, right? So instead of doing things like if something return true, okay, this is right, this is not even example, actually you can just do return something, right? I mean, like if something a plus plus, right? Or if not something a plus plus, so you can just avoid doing that, and you can write it something like a plus is equals to something, right? Because something corresponds to 1, right? So when it is added to 1, it is typecasted to an integer data type, and the typecasting would make this a value of 1. Same goes for negative numbers. You can write a plus is equals to 1 minus something, right? So 1 will always be treated as an integer data type, right? Something will be typecasted, right? It will be 0. So this was the alternative form of if not something, right? If not something, a plus plus. Now if you see if not something, that means something is 0, right? So 1 minus 0 will give 1. Ultimately you are adding a plus equals to 1, right? Now coming from this, I have a very small trick. Let's say you want to again, this is a very neat trick, and this is I found in one of the solutions that I was reading. So say you want to alternate between two different numbers, that is a and b, right? So instead of writing something like if number is a, number is b, else number is a, or even let's say you say okay, instead of that I'll write a ternary number, if a then write b else a, right? I'll give you a very concise thing. Let's say, let's take the sum of a and b, let's say k, okay, and this will be, you'll understand it immediately. You can always write number is equals to k minus number, right? And this is how you do swapping as well, using using without using an extra space, right? So if number is b, this will become a plus b minus b, which is ultimately a. If number is a, number will become a plus b minus a, which is ultimately b, right? So basically you're swapping the numbers, right? Without using any extra space or something, or without writing that big conditions. What are you using? You're just summing it up, right? And sum minus that number, like always return the other number, right? Again, this is used in bipartite checking in graphs. We want to alternate between zeros and ones, so you just do 1 minus color is equals to 1 minus color, or to check maybe if color is equals to 1 minus color. No, sorry, it's just an assignment. This something like this. So again, we'll come to that, and not just this coloring. Usually for graph coloring, you can use things like this, right? But this is mostly for alternating between two elements, though, not for more than two colors. Okay, I think these are actually very small tricks. Okay, very small things that can make your code more precise, right? It might not matter if you are if you're in development, right? If you're developing things there, it's better to write a more elaborated code that is more verbose. But during interviews, it will always be better to write a concise code, right? Say even in development, like you can always cut down few things, right? But again, that depends on a lot of things, and let's not go in that domain. So this is where like these were the few tricks. You can always come and watch it again, right? Okay, somebody left a comment. Rishabh says, can we do this using k is equals to a XOR b, where num is equals to k XOR num? You can only do that if the numbers don't share a common bit, right? Say a is equals to 3, b is equals to 1, right? Then can you see that your answer fails? K is equals to a is or b, then k is or num. K will be 2. Wait, let me see. Num is equals to k is or num. So if num is 3 initially, num is equals to 3 is or 2. Yeah, this will give 1. Yeah, I think, yeah, you can do that. Sorry. Because zoring the number, yeah, it's basically the same thing. It follows the same property, right? So a plus b, it follows the same property that a plus b minus b will be a. Similarly, a zor b, a zor b will give a, right? It just follows the same property. Yes, you can do that as well. Nice. But again, like, prefer more simplistic things, right? It's fine if you understand zor more, you can do that. But mostly I've seen using addition, subtraction. But yeah, even zor is nice, right? Okay. And actually, zor takes care of domain as well. So a zor b can never be greater than both. Can never be greater than maximum of a and b, right? So it will never cross the domain. So actually, this is better if you're trying to cross the domain, right? Or if it crosses the domain somehow. Alright, so I'll just talk about some STL functions in short, and I'll be very quick with it because people using Python don't really need it. Okay, now some STL functions are, say we have a function called count, okay, which can, given a range, it will count the elements in that. So say you are given a string S, you are given a string S, A, B, C, D, E. So you can write int count of A's is equals to count s dot begin, s dot end, and count a, right? Things like this. Now, why is count function useful? Even in Python, try to find an alternate for this. Okay, but how is count function useful? So you might have seen problems where you have to check whether the number is vowel or a consonant, right? And how do you do it? Do you do it something like this? If character is equals to a, or character is equals to b, or character a, e, I, o, u, complete thing, right? You see, that's very hectic, right? So what if I propose a new solution? I write a, e, I, o, u, and I say if count of s dot begin comma s dot end comma whatever character you are checking, just this. Okay, now what happens if this character exists in that? You're doing a vowel check. If a exists in this, it will return a count of 1, and 1 is treated as a boolean, so this condition will automatically return 2. So you can just write cout vowel, right? So things like this. Then again, even for some different kind of questions, we have to check if this character belongs to that, right? Give me a second and drink some water. Things like this. This is a very neat trick for vowel check, and in some very special problems, right? Apart from that, we have an operator called merge. Okay, if you want to use it, I'll recommend you to go and read about it first. There are 5 different parameters in merge. Okay, and merge function is basically what merge function in merge sort, right? So after you have some sorted arrays, 1 2 3 4 1 4 6 7, 2 different sorted arrays, and you want to merge them into one, you can use the merge function. It will merge them into one. So essentially make it 1 2 3 4 4 6 7, right? Then there is one function called unique. So unique function is also a very good function in STL. Like, see, there are a lot of functions. I'm just talking about the special ones, right? You can always keep using and you'll find a lot of special ones yourself. So what unique function does is, given an array which is sorted and has duplicates, right? Unique function actually turns this into this, right? And the remaining part is left as it is. So first 5 elements are turned like this, and remaining part is left as it was there, and it returns you this iterator, the last iterator of the unique path. So you can always resize it based on the iterator, and then you can get the unique elements. Again, you can go and read about it, right? Understanding how it works requires two different functions to work together. Unique, go and read about it. That's fine. Again, another one special function in STL is called partial sum. Okay, and partial sum is basically prefix sums. Okay, the way you make prefix sums, right? A of I plus equals to A of I minus 1, right? A of 1 is sum of A of 0 and 1, 2 is sum of 0 1 2, 3 is sum of 0 1 2 3, 3 sum of, yes. So you can just do it using partial sum. You can give what array you want to sum and where do you want to start. So in that case, if you are prefix summing in the same array, you can just give it something like this. So it will create the prefix sum itself with partial sum, right? And you don't have to do it manually. This is also a very good function. Similarly, there are functions like back, front, gives you the back and front of say a string or a vector, right? Not for sets. Okay, sets and maps, that's different. Again, you might be having something like this in Python as well. So make use of these actually. Instead of writing a of a dot size minus 1, use something like a dot back. That's a lot easier. A dot front is 0, a of 0, so anything is fine, right? Again, in this is both in Python and C++. Make extensive use of lambda functions. Okay, even in C++ we have lambda functions now. Python we had lambda functions from long ago. So I'll show you how lambda functions are written. So this is equal to uh, auto save function is equals to, you give an ampersand, you take what all parameters you are accepting, right, and you write the function and you return whatever you want, right? Return true, check something, return true, right? Taking these parameters. Lambda functions are basically are mainly used for custom comparators, right? So while you are trying to sort array, you can give a custom comparator here based on the data type. Say it is an array of integer a and b, you can give return a less than b, right? And this will essentially sort your array based on increasing order. A greater than b sorts it the other way around, right? So things like this. So make extensive use of lambda functions, because lambda functions can access elements that you write inside a function, right? So x is equals to, and so this works. This will give no error. You can always access this in element. So it is very easy. Say if you want to, if you're traversing a grid and you want a function that checks whether you're not jumping out of the grid, so you can always use the lambda function for that, right? To write the check function. Okay, cool. Now one last thing about C++, there's something called a bit set. Okay, now it's not something very important, right? But if you enjoy reading, you can go and read about this. So basically, there's this bit set of size. Okay, even I don't know like how exactly it's written because it's not very common. Okay, so bit sets, how bit sets are useful is that, again, I told you about bitwise thing, right? Bitwise thing is a lot more efficient with compilers, right? Same goes for bitwise bit sets. So bit sets are actually something like 64 times faster than normal sets or vectors. So at places where you just want to store zeros and ones, right? 0 1 0 1, right? Say a visited array, right? Bit sets are a lot more powerful. Bit sets can even support shift operators, so you can shift the entire set at in one direction, right? Like just like say there's a bit set called set, so you can do set is equals to set left shift 1, left shift 100, whatever you want, right? Again, bit sets are very useful in in DP programs like subset sum, right? Because they are very fast. So with bitset you can also write O 10 raised to the power 8, O of 10 raised to the power 8, and it will still pass. I think it's into 8, and this will still pass, right? Because bitsets are very again, they use bitwise operators and they are very optimized for compilers, so they are very easy to parallelize. So they just do n by 64 or something, right, based on number of bits. Okay, that's all. You can go and read about bitsets. Bitsets are fairly new, they just came out right now. Okay, so that's all for tricks. And right now what I'll try to do is I'll try to solve one or two problems based on how much time we have. Right, I won't solve it, I won't code it, but I'll tell you how to approach a problem. Right, so I'll stop presenting and I'll wait. Okay, so first problem will be this. I'll send you the link. Cool. Okay, you can either read the problem or I'll read it to you. So okay, I'll read it to you actually. So the problem says you're given an array B, okay, and the an anonymous informant has told you that B was obtained as following. So initially there existed a different array after which the following two component operation was performed k times. So these two operations are component operation. That means these two are a part of the same operation. So given an array A, what was performed? A fixed point x was chosen in an array, and then array A was cyclically shift left exactly x times. Okay, so what is a fixed point? So they say a number x is called a fixed point in the array where if ax is equals to x. So basically, if in the fourth position you have number 4, that is a fixed point. Okay, so so for given array A, we chose a fixed point and we left shifted the array that number of times. Okay, now as a result of k such operations, the array B was obtained. You want to check if the words of anonymous informant can be true or if they are guaranteed to be false. Right. So again, I'll repeat the question. So in this question, you're given an array B, which was the result of some operations done on A. Okay. And the operation that was done was in A, a fixed point was picked. A fixed point is a number that is a form like A of x is x. Okay. For a one based indexing here. Right. And the array was left shifted that many times. Right. So after k such operations, the array B was obtained. So you have to verify, does A exist such that after k operations this B was obtained. Right. So they have given a few examples. So 5 is the length of the array, 3 is the number of times we have performed the operation, and this is the B array. Basically, this is the resultant array. Right. Wait, I should actually share my window. Meet. Oops. I have sent the problem link. You can go and read it. Okay. So this was the problem. Okay, so for the example 5 3 4 3 3 2 3, 5 3 4 3 3 2 3. Okay, remember this is A. So you have to say, did there exist? Sorry, this is B. Sorry. So you have to say, did there exist a such that after performing that given operations k times, where k is 3, you can obtain this array. Right. So the answer says like explanation says the first array was 3 2 3 4 3. So in this case the array could have been 3 2 3 4 3, where they chose in the first operation fixed point was x equals to 2. So they chose this as a fixed point. You can see that this is in the second position and is the second element. Is the second element and the magnitude is 2. So this is a fixed point. So rotated it 2 times to the left. So this became now 3 4 3 3 2. Right. 2 times 1 2. Now after 2, this was the array. In the second operation, fixed point was x equals to 3 was chosen. So this is now a fixed point. Now again we rotated it 3 times. So this becomes 3, 2, 3, 4, 3. Now you can see the array became this, and third operation, fixed point, x equals to 3 was chosen. So this became 3, 2, 3, 4, 3. And if you see, this array is the array that we are given in the question, right? So basically the answer for this test case will be yes, it is possible, right? But the thing is, you're not given A, you're given B. You have to verify, is this possible? Okay, I think we'll just be able to cover this one problem. Okay, now I'll explain you how to think about this problem. I'll give you 1 minute or 2 minutes to think about a solution, right? Please don't check the tutorial. And if you want to share your solution, you can just open your mic and talk to me. Or if you have an idea. I share the Jamboard instead. Alright. So this isn't a very easy problem if you don't break it down. Okay. Now okay, how will I start thinking about it? Now every time I see such question, I think about the operations. And I try to find if there's something I can find from the operation. Right. So I see the operations are it's you have to pick a fixed point and you have to rotate the fixed point left by that many times, right? Now what might happen if you rotate a fixed point? So say you have some array a b c d e, and if c was a fixed point in this array, it would obviously be 3, right? Now I'll try to rotate it, right? To solve this problem, I'll try to rotate it, and I'll see that upon rotation it reaches here, right? Okay, it reaches here, fine. Now say E was a fixed point and E was 2. I'll try to rotate this and I'll see where 2 is reaching again. I'll find that 2 is reaching the last position, similar to what last point of rotation was, like where it reached, right? Now something that you can decode, and we can find a pattern. Always find patterns to decode, right? A pattern in this question is, every time you rotate a fixed point to its left, it will always reach the last position. Why? Because it is that much positions from the front, right? If the fixed point is 4, it is 4 positions away from the front. So if you do 4 left rotations, it is bound to reach the last position, right? No matter what the fixed point is. If the fixed point was 1, and whatever the array is, rotating this array once will always make it reach the last position. Had it been some 15, it will always reach the last position after 15 rotations, right? So you know where to start. So given B, you know that the last rotation had been from the last element, right? So the last element was rotated. This is what I'll think, okay, because I found a pattern. Okay, now I'll try to decode it, right? Okay, so last element could have been the element that was rotated in the last operation, right? In the kth operation, right? So what I'll do is, I'll instead of simulating and rotating the whole array, okay, this was the, I think, exact problem I was talking about. Instead of rotating it k times, I'll try to find out what would have been the last element before this operation. So if this came this way, the opposite will be this way, right? Right. So you have to check the opposite because you're doing the operation backwards now. So if this is 3, I'll check what is the element 3 steps away from it. Right? Because if you left shifted the array 3 times, that array might have been this element might have been the last element on the k minus 1th operation, right? Like 3 would have been here, some number, and this element would have been here, right? Some number, and this element. So this element would have been here in the k minus 1th operation, right? So I'll have this number, then I'll go back that many times again, have a different number, and I'll do this k times, right? So that I come to all the operations, and I know like in each operation what shift was performed, right? Now one thing to realize is that any number, okay, now you can look for a corner case now, right? Now you are satisfied with, okay, the last element is always the element that was shifted, that was a fixed point. Now tell me what cannot be the last element. A last element was a fixed point. What cannot be a fixed point? Any number that is greater than the size of the array cannot be a fixed point, right? In an array of 5 elements, how can 15 be a fixed point? Cannot be, right? 1, 2, 3, 4, 15. 15 doesn't occur in the 15th position because there is no 15th position in the array. So the only thing to check was that the last element that you are getting in k operation should be less than equal to n. If otherwise, you can say no, it's not possible, right? Now, okay, this is fine. This is perfectly fine. You decoded the pattern. You found the case for no, right? And if none of the no's, like if you don't get any no, it will be a yes. Okay, but now you found another problem. The problem was k is 10 raised to the power 9, right? And what did I tell you? Anything less than 10 raised to the power 7 will do, but you cannot simulate it 10 raised to the power 5 times, right? So now what to do? If you try to do simulate it 10 raised to the power 9 times, you'll run out of time probably, right? So now explain me this. What happens when 10 raised to the power 9 operations are performed? Now this is what I'll think about. Like in an array of 10 raised to the power 5 elements, okay, what was n? N was 2 into 10 raised to the power 5. Let's take it 10 raised to the power 5. In an array of 10 raised to the power 5 elements, how many unique rotations are possible? Just 10 raised to the power 5, right? At maximum, 10 raised to the power 5 unique rotations are possible, right? So how can k even be 10 raised to the power 9? There is only one case where it can be 10 raised to the power 9, where the array can be infinitely rotated, right? Something like all the elements are same. What happens? This is a fixed point, you rotate it, get the same array, again fixed point, rotate it, same array, again get the fixed point, right? But there is one more case. This is not the only case. There can be cases where the thing is looping, right? Say if this is the fixed point, this goes to the end, and then this comes front, right? And then this is also a fixed point when it comes front. So something like x, y, 3, z, 2. If you pick 3 as the fixed point, the array will look like x, y, 3, z, 2. If you pick 2 as the fixed point, it will become z, 2, x, y, 3. So you are seeing a cycle, right? And basically what is happening, you are again revisiting the same index. So the only change now required here is you can perform all the operations if the index that you are looping is visited, right? You are jumping indexes, right, to check for the condition. So I ran out of pages. Okay, anyway, so the index that you're checking every time should not be visited again. If it is visited again, you're assured that it's a cycle. And if there is an answer exists for k greater than n, and it's a yes, say it's a yes, there is bound to be a cycle, because you cannot have more than n unique shifts if it is a n unique shifts, if all of the shifts are possible, right? And if it's possible and you are having it more than that, that means that there is a cycle, and then k can be infinite, right? Because if there is a cycle, you can keep on shifting, keep on shifting, keep on shifting, right? So, or let's break it down even further. What if I tell you it is this optimal to check just for n shifts, right? If k is greater than n, just make k equals to n then, because if it can shift for n times, right? If say every n time it is having a unique shift, right? Or it can perform the operation, that means that it will cyclically come back, right? If for all the n operation you are able to find a fixed point, and say if all the n are unique, or even if it's not unique, right, then you can easily say, or that is enough to prove that it can do this infinitely, right? Because if you can get all the unique shifts, it will always be possible to shift it more than n times, right? So every time k greater than n, you just make k equals to n, and then check the complete thing again just for n. Now this time O of k will work because it's equal to n, right? So even if you don't maintain a visited array, this will work, right? So I think we just got time to discuss one problem. If you want to ask anything, I think I explained things in a hurry, right? This problem has a lot of things to it, and might have given you time to understand as well, but okay. Okay, if you want to ask anything.
Can you repeat like how you make k equal to n from k greater than n?
Yeah, so I'm running out of pages. Uh, so say in the best condition, so in this condition you saw that even with n equal to 5, in just two operations we are getting a cycle, right? So tell me what happens if n is equals to 5, or n is equals okay, n is equals to 5 and k is also equal to 5, and you are getting the answer as yes. What will happen? See, there is like it is bound that there will be a cycle if k and n is equal, or okay, how do I explain this? See, there is one thing this, right, that there are n unique rotations, right? And mm, so okay, so here this, say every operation we picked a unique index and we rotated it using that index, right? So if we have tried it for every index and every index is valid, right? Every index 1, 2, 3, 4, 5 can be rotated, then you can infinitely rotate it, right? Because all of them are valid. At some point, some index will be at the last stage, last position. Say 4 is at the last position right now, and say 4 is not an invalid case, right? It is less than equal to n, so it is possible to rotate it. Say for this array, right? This exact array, right? This was given as b, so 5 is possible, right? And if here it was not 5, say it is something else, say 5 and 4. So 4 it's possible to rotate, then some other number will come in the back which will always be less than equal to n, right? Then again that rotation is possible, then some other number will come, that rotation is also possible, right? So if for every unique n you have checked it, right? If for every unique n you have checked it, you can just safely say that okay, all the numbers under the array can be rotated. But okay, so there is this intuition that you have to come up with, is that if you have checked for n possible rotations, in the best case or in the worst case you'll have checked all the indexes, in the best case you might have started looping even before checking everything, right? So either, so yeah, the whole thing is, after checking n operation, either of the two will happen. Either you'll find a loop, right, or you will have checked all the indexes and all the indexes are valid, right? Any of this will occur, and in both of the condition you can get the answer as infinite, because if all the indexes are perfect and fine, you can always say, in this case, if all the indexes are valid, you can keep on rotating the array. Or if you found a loop, then again, say something like this. You found the loop, so you can keep on rotating it infinitely, even if other indexes are not valid, because you won't even come to them. Right, here xyz, you don't even care if they're 10 to the power 9 or something, because you will never come to them. You'll just keep looping between 2 and 3. So again, by checking n possible, and like by checking n steps, even in the worst case where you have to check each and every number, if all of those are valid, then you can safely say that there is a loop, and this can go beyond n as well. And if you find a loop earlier, you'll keep on looping the loop, right? You'll keep on going inside the loop. So for n operations, maybe you'll just check 5 elements, but all those 5 elements are looping around. So you can say, okay, you can keep on looping again. So basically, with after checking n elements, you are sure that you are going to find a loop. That's all. And if you're not finding a loop, you are getting a no. That's all. Either it will be either of the case. You'll find a loop and you'll say yes, it's possible, or you'll say no, it's not possible. Uh,
Yeah, got it, got it.
okay, cool. It's a bit hard to understand right now, but again, after you've solved a lot of problems, after you have like found the intuition for a lot of problems, it will be easier to understand. And this will be in one of our problem sheets in the course. So let's see if you can remember up till then. If you have any doubts, you can please speak with me, or you can leave by 10:30. Then it's already very late. Yeah, did they choose the fixed point randomly or the first one? See, how they chose it is not told. Okay, it's just said that you want to check if the words of informant can be true, or if they are guaranteed to be false. There can be multiple different orientations for this, right? But I proved that the fixed point that was rotated came to the last index, right? It came to the last index. So we know exactly what they chose. Even if it's not given, even if you start with A, there can be multiple fixed points. But if you are coming back from B, you know that this last point was the last element was the chosen point that was rotated, right? So it doesn't even matter how they chose it. You know what has been chosen. This was like how I think about the problem. And okay, right now I won't start with solving problems like this. It's hard. Even if I give you this, I'll help you understand it and won't expect that you can solve it immediately. But we'll will be solving a lot of problems, and at some point you'll find problems like this not very hard to think of. Okay, and there are multiple such problems there. And also tomorrow same time we'll be doing some code forces problem, okay, hands on. You will be doing, I'll be explaining, right? And again, I'll just make a temporary tracker sheet where everyone who is here, you can just keep on posting your solutions, and I'll either review them, or I'll have a or we can just have a friendly competition, like who is solving questions first, right? So we'll be having like 10 questions, right? And I'll give you certain time to solve some problem, solve each of those, right? And it starts with very easy problems and it keeps jumping to harder and harder problems. Alright guys, if you don't have doubts, you can leave. I'll stop the recording.